Yeah, I also hope that this should be like an expert user, but I'm not sure actually. And I have like many things to show, but I'm not sure also if we'll have the time to do it. But
I will remind you of the time.
no, yeah, I would like to recall that. Yeah, thank you for inviting me to this conference, and I will talk more about my work that I've been doing in Finland, part of Finland, and now part in Dresden. And mainly it's also an development, yeah, and in yeah, GW and RPA, random phase approximation, but also in the NOMAD library, the GreenX. Okay, so let me go to the outline of this presentation. I will just briefly give an introduction about GW, and then what about the GreenX library, and some conclusions. Okay, so let's go quickly. So in electronic band structure of materials, the workhorse of for this calculation is the DFT, right? So in this example, I wanted to show that for this material, if I remember correctly, it's gallium arsenide, you perform a calculation, the level of DFT, and you can see that the bands, the valence and the conduction bands are overlapping. But then you go to an experiment, and actually the experiment says that there exists a band gap. So what is wrong with the DFT calculation? There are many explanations, but I wanted to point out that this is the experimental result, and also this is the band gap calculated with GW. And you can see GW can reproduce the experimental band gap. So I don't want to convince you, but this is my work, my motivation. So in theoretical spectroscopy, yeah, we can have these two effects, that is the removal of one of the electrons or the addition of one electron, right? And then in molecules, we can see as the ionization energy, so the energy that we need to take out an electron. And here we can compare in this plot that PBE and also all other DFT calculation, they are quite far away if we compare with experimental. And then different flavors of GW calculation with different initial points, they are getting close to if we compare with experimental. In this regard, also for periodic system, we can see here that DFT calculation, they are quite far from this line, that is the experimental one, and then different methodologies relying on the GW calculation, they are getting close to the experimental results. So this is our motivation to continue to do GW. So yeah, let's use it. That's it. But it's not that easy, actually, because currently, I will say currently, because there are a lot of development, recent developments. So one of the main points is that the GW calculation show a poor scaling with system sign. It means that we are limited to a few atoms in molecules, or limited to a few atoms in unit cell for solids. And also, it's high memory demand, so the computational resources that you need to perform GW calculation, it's heavy. Yeah. So even if we are taking the advantage of the HPC, this picture is from LUMI, the HPC system in Finland. that we had the opportunity to play with, right? But we realized that it's not that easy to go simply to add or ask for more resources or for more memory. It can be also a waste of time or work. So let me go a bit on the GW approach and to explain why we are doing certain developments to the GreenX. I will not go into the details, but here is the formulation of the GW. So in principle is a correction to the DFT or to the ground state, right? And one important quantity that we need to compute is the polarizability, in this case in the imaginary imaginary frequency. And this quantity I mark in red is the one that it costs too much in the GW calculation. So this is scale n to the power of 4 with system size. And so the rest of the steps is they scale n to the power of 3. But so we need to think how to solve this problem first. And then we can use different approaches. I will talk here about the resolution of identity. It's just a different way to rewrite this. Oh, I don't know. Again, to rewrite this equation. So in the original formulation, 4 center coulomb integral scales n to the power of 4. So if we use the resolution of identity, we can rewrite this quantity into sum of products of 3 center and 2 center electron repulsion integrals. So with this technique, we lower down the formal scaling to n to the power of 3, right? So, and then if we use the resolution of identity in the GW approach, so this is the final equation for the polarizability, in this case in the auxiliary basis functions, but at the end we still scaling n to the power of 4 because there are two sums here that are entangled, we cannot separate, right? So to avoid this, well, we need to ask what we can use to speed up GW calculation. There are many other flavors of resolution of identity, and also I will talk about the time-space GW that it scales n to the power of 3. Okay, so how we can overcome this n to the power of 4 scaling in the canonical GW implementation? In here, we can rewrite the green function that at the beginning was in imaginary frequency, and if we rewrite it in the imaginary time, we can compute the polarizability in the imaginary time just by the direct product of these two Green's functions. And here they are already these sums that at the beginning were entangled, now they are separated. So this operation at the end costs n to the power of 3. And the rest of the operation also costs n to the power of 3. And then there are here, I will show later on, there are some transformation that we need to go from time to frequency, and then we need to go from frequency to time, and then from time also we need to go back to frequency. There are more operations, but the prefactor of this operation are small. Okay. So in order to get this transformation, we need to have a specific matrices to perform this transformation. So saying that, we came to the idea that these tools that we need, they are also used in I mean, we need to use it even if I'm developing for FHIMs, but also people who develop Avinit, Exciting, but they are the same formulation, just a different implementation. So we need, at some point, the same tools to perform the GW calculation. So in this regard, for the NOMAD and the Word Package 2, it's called X-scale Green function-based method. So they are here involved four different codes, and we realized that there are tools or operations that are independent of the software, and there are also that are dependent of the intrinsic of the software. So. But there are some of them that we can share somehow. So, and then, this is the Word Package team meeting in Kayani. We visited Lumi, the installation of Lumi. So, so we are working close together. And then for this, operation in which we need to go from time to frequency, or for frequency to time, and also from frequency to time. So we need to provide these tools. So we are then in Word Package 2 developing the GreenX. It's a library that provides all these cosine and sine transformation to just simply go from one space from time to frequency, or the frequency to time. So we already published this component of the GreenX last year, and this is. I wanted to show the advantage to use we call minimax, right? In molecules and also in solids, this is RPA correlation energy. You can see that we have a better convergence if we compare with a classical Gauss-Lejean or the modified Gauss-Lejean grids, frequency grids that is used for GW calculations. So if we want to have like a threshold, let's say 10 to the minus 6 in energies, that is really good. So we need only 12 or 14 minimax points, while for modified Gauss-Lejean we need around 46. Yeah, so this is like we decreased that 3-4 times the time that we need to perform the calculations and to get accurate results. So this is also been tested in this this is in molecules, the TL set, and also we see that after 20 minimax points, we already have converged results. And in my recent work, I also now have working low-scale RPA in FHIMs, and also there are some still errors that we are carrying. But we can say that errors below are below the milli eV, milli electron volts, and so sub-milli eV. So it's enough to have accurate results. Also, these minimax grids has been using for low scale in GW. like here, we compute the HOMO of the GWTL set, and also you see the quite fast convergence when we increase the number of minimax points. Usually in a calculation, in GW calculation, you want to have like this convergence in this range of the below milli EVs. In Gauss-Lejean or another different grids, you need at least 60 or 100 points to converge. Also, in Abinit, they also have a low scale in GW, so it's been applied for solids, and also after 20, 30, let's say 20 minimax grid points, we already have converged results. So also these results has been published just recently, like 2 weeks ago. And then also in GreenX, we are developing localized basis component. In this case, it's an implementation of low scale in GW. I will not go into the details, but here we are using a specific way to build the polarizability in real space. And then we are also using the time frequency grids that provides the GreenX so to perform the RPA calculation. So we are just using all the tools that we have. Yeah, just to mention that this also was part of my work, is to implement the separable resolution of identity in FHINs, but also it's already in the GreenX library. Yeah, you can use it. You can use this tool. Yeah, and only to mention briefly or quickly that this resolution of identity relies on compute the fitting coefficients into a real space grid. And this allows us to reformulate the GW in a space-time right away, or in a more easy way than the normal resolution of identity. And then I implemented in FHIMs, and I also validated and benchmarked until around 100 number of 100 atoms in these carbon clusters. And yeah, we can say that in many correlated methods, if we use the separable resolution of identity, we have errors below to milli EV, 1 milli EV if we compare the global and separable resolution of identity. So we're still getting accurate results of preserving the accuracy of the resolution of identity. And yeah, this is a recent news that I implemented in the space-time RPA correlation with separable Ri, and you can see that if we compare with the canonical implementation, the difference are also 10 to the minus 5 if we compare 10 to the minus 5 milli-electron electron volts per electron. So we're still preserving the accuracy from the canonical and the space-time RPA. Okay, I will go quickly on this. So another component that we are developing in the GreenX is this called analytical continuation for the self-energy in the GW. It is computed in the imaginary frequency, but at the end, then the quantity that we need is let's say living in the real space, right? Not in the imaginary part. So we need to analytic continuate the self-energy. So with this, we use the Padé approximation. Oh, there are many approximations, but in FAIRmat we use the Padé approximation. And also, for core level GW, the screen Coulomb interaction can also be analytic continuate. This is a combination of the contour deformation and then the analytical continuation of GW of W. Yeah. So if we combine both, this is work from Dorotea Golce and Ramon Panades. Yeah, they validate that the combination of these two methodologies, we can still get accurate results for the core, say, 65, or also in GW, GW100 set. What is the advantage of this method is that for core level, usually the scaling into the number on the system is n to the power of 5, and then we can lower down almost into power of 4 with this methodology. So when we were analyzing this problem, we saw that the analytical continuation, at least in the Padé, it's quite unstable. Yeah. Okay. Yeah. Okay. Yeah. It's quite unstable. So. So we worked in to get a better Padé approximation with some corrections, and this analytical continuation that it not only used in GW, now is also available in the library in GreenX, and yeah. So until here. So everyone can, or every code can access to these developments, the minimax grids, and also the localized basis component, and here the analytical continuation. And there are other components that are also developing for plane waves and also for LPDW. I don't remember the, yeah. And exciting. So we are trying to build more tools for DGW calculations. And well, for the data availability, all the calculation that we perform in this GW and RPA calculation, we uploaded in the NOMAD repository. They are available on these DOIs that provides by NOMAD. And also we already talked with Chema to how to improve the GW part of the analysis in the NOMAD repository. And yeah, with this, I wanted to reach to my conclusion that I already said. We have the minimax frequency grids provided in our library, and also the separable resolution of identity is available in the GreenX, and yeah, also the analytical continuation, a more stable analytical continuation, it's also available in the GreenX library. And yeah, I would like to thank to my team in Dresden, and also our collaborators. There are many, some of them probably they are here. And yeah, the fundings, the software that we are using, and also the computational resources that we got, we use it a lot. Thank you.